Let's talk about measures of variance. I gotta make the slideshow move. There we go. So we're going to talk about variability and how it's used to describe our data sets. And then we're going to talk about how to compute range, standard deviation, and variance, and the differences between standard deviation and variance. They're similar, but they're different. So we talked about central tendency in the video just before this one. And remember that it's a way to describe the center point of a distribution for any data set, whatever data set you have. It's the way to describe the center of that distribution. Well, variability describes how the data are spread out. So if you look down here at the bottom, this picture that I have here, this is showing like the size of fish, right? Large fish, small fish. So let's say this is like a fishing boat. These fishing boats are in two different areas of the ocean, and the average fish size is 50, I don't know, centimeters. What size are tuna usually? I'm not a tuna measurer, so we'll just say 50 centimeters. I don't know. This is like a totally, not even a ballpark guess. Who knows? Let me know if you know. Anyway, you can see that one boat that's described by the blue distribution, the average is 50. The brown distribution, the average is 50. So they're both coming up with an average of 50 centimeter tuna. But the boat that's described by the blue distribution is pulling up a lot more fish that are closer to 50 centimeters. It's more unlikely for them to get really large tuna or really small tuna. Now the brown boat down there, they have a much larger distribution. There's more variability. The data are more spread out. It's more likely for them to pull larger tuna. It's more likely for them to pull smaller tuna. So we can have a central tendency measure that is exactly the same, but the variability may not be the same. You can also think of it like this. Let's say the brown boat moves to a different part of the ocean, and here, these tuna are just, almost all of them are 50 centimeters, or very close, right? And so now our distribution has really shrunk down. There's not a lot of variability around 50 centimeters. It's very tightly clustered. When you use central tendency and variability together, you can pretty much describe the distribution that you're dealing with. And we're assuming that this is something that's normally distributed, so we have an idea of the shape of it. And so then when you give us central tendency, variability, well, we know exactly, we can picture in our heads exactly what this looks like and what we can expect from it. There's a couple different measures of variability: range, standard deviation, and variance. And we're going to talk about those and how to compute those. So the range is quite literally the range between the highest and lowest data points. We've got two different sets of data here: 1, 2, 3, 4, 5, 6, 7, 8, and 5, 6, 7, 8, 9, 10, 11, 12. They've got the same range, right? They're different data. They'd have a different mean. In fact, the top one, the mean would be 4.5, and bottom one, the mean would be 8.5. But that doesn't mean that the range isn't the same. The range is the same here. How do we compute the range? Well, we'll talk about how we compute the range in a second. But you can see that these have, there's the same amount of numbers. There's the same distance between the beginning and ending numbers here. We'll talk about how to compute them in a second. Standard deviation, this is our most frequently reported measure of variability. You typically see in papers, if you're reading it, the average or the mean. Usually we call it the mean in papers, and then the standard deviation. What it does is it measures the spread of data around the mean. Standard deviation of 0 indicates that all the values are identical. So like, let's say on a questionnaire, everybody said yes to something. That's not a very good. Let's say it's a scale, 1 to 10 scale. And let's say everybody really didn't care about what they were talking about. So everybody gave it a 5. It's right in the middle. And every single person rates this as a 5. They neither like it nor dislike it. and that would have a standard deviation of 0. All the values are identical. As the standard deviation grows, though, that means that there's a lot more variability. So if people gave it 4s, 5s, and 6s, you'd have a larger standard deviation than 0. And then if you had some people giving it 1s, some people giving it 10s, and everything in between, you'd have a much larger standard deviation. We abbreviate standard deviation as SD, STD, or STD-DEV. You're going to see all of these. SD is the one that we usually use in papers. So you'll see M equals blah, comma, SD equals blah. STD and STD-DEV, these are ones that you'll see in usually coding. STDEV is the one that we're going to use in Excel. And then, the history of standard deviation just is not as fantastically cool as the history of the mean. I think it's safe to say that standard deviation was rediscovered by Francis Galton in 1860. When we can trace the mean back to quite old BC, I feel like probably someone at some point had realized that there were things like the standard deviation or variance or something like that that we could compute. But in the modern era, the standard deviation was developed, rediscovered, something by Francis Galton around 1860. Now, Francis Galton, if you're one of my speech and hearing students, you might know of the Galton whistle, which is used to test hearing. It's also used to test hearing in animals, too. This is basically a dog whistle or other whistles with high pitches, but that humans can hear. Some are so high that they can't. He was a pretty interesting guy who developed some really cool things and also had some really, also did some really not so cool things. But anyway, you can check that out for yourself. Variance is the square of the standard deviation. That's it. It's the square of the standard deviation. It measures the spread of data around the mean, just like standard deviation. A variance of 0 is going to also indicate that all the values are the same, just like standard deviation. Also, just like standard deviation, the larger the variance, the larger the variability. Really, the main difference here is one is the square root of the other. Standard deviation is the square root of variance. That's the main difference between the two. Variance is abbreviated as VAR. You're going to see this in Excel. You'll see it in papers sometimes if it's used. But again, standard deviation is the most common. And here are other notations that you might see. Again, going back to what we talked about last time, little n is a sample stat and large N is a population parameter. Similarly, for standard deviation, we have lowercase s. And if you're talking about variance, remember variance is just the square of the standard deviation, so it's s squared. Easy. Population parameter, this is a little different. We've got another cool Greek letter here. It's sigma. It's a lowercase sigma, because you remember that sigma also means to take the sum of everything. That's the big one that kind of looks like a pointy E. That's uppercase sigma. And again, it means take the sum of. Lowercase sigma implies that it is the standard deviation of a population. You'll see it as sigma. Sometimes you'll see it as sigma sub x. And then variance, again, just like s and s squared, you'll see a population variance as sigma squared. So these are other types of notations to know. There's a lot of different notations for one thing, but it's good to know them all so that you can kind of orient yourself to what you're looking at, what you're reading. Different scientists, statisticians, researchers are going to report these things slightly differently, and so that's why you have to know them all. Okay, so let's talk about actually calculating these measures of variance. Of course, like last time, we can do it by hand. You can also do it in Excel. We're going to talk about by hand first, but once we talk about Excel, you'll probably never do it by hand. But it's good to know, right? So we have two types of ranges. We have an exclusive range and an inclusive range. We'll talk about that in a second. But the formula for exclusive range is the highest score minus the lowest score. It's just that easy. The inclusive range is pretty much the same thing. It's the highest score minus the lowest score plus 1. Why is that? You'll see. You'll see. Exclusive range is the one that we most commonly use. So when we say range, it usually means exclusive range. In fact, I would go so far as to say that when you see range, it is exclusive range. It will be called inclusive range if it's not exclusive range, right? So range is essentially synonymous with exclusive range. Again, in most papers that talk about the range of a data set. Okay, so let's calculate this. Basically what you do, you take the highest score, take the lowest score. You're going to subtract the lowest score from the highest score. In this case, we have 48 and 98. So 50. 50 is our range. Again, this is an exclusive range, but that's the most common one. Okay, now why is there a difference between exclusive and inclusive range? If you're a smart person, if you're a real smarty pants, you may already have caught why this is why there's a difference between exclusive and inclusive range. But if you haven't, that's fine. That's okay. But I'll tell you. So take a look at this set of values down here at the bottom. 5, 6, 7, 8, 9, 10, 11, 12. So how many data points are there? There's 1, 2, 3, 4, 5, 6, 7, 8. All right. But what's our range? Well, it's 12 minus 5, the highest minus the lowest, which is 7. So we have 8 actual data points, but our range is 7. Exclusive range. Remember, the formula for inclusive range is highest minus the lowest plus 1. So when you do inclusive range, it's basically the same as counting every individual item. And when you do exclusive range, you're just subtracting the lowest from the highest and taking that. So again, typically we use exclusive range, but that's the difference between exclusive and inclusive range. Okay, now we're going to talk about calculating the standard deviation. There is a difference here. With everything else that we've talked about, it's pretty much the same. Population or sample, it's pretty much the same. But we're actually getting into the area where we're going to see some differences. So take a look at the left. This is the population standard deviation. So sigma equals the square root of all of the added deviations from the mean squared. Let me, you know what? Let me get my, oops. There we go. Okay, so we take the square root of what's coming, everything that we have here. So this is the deviation from the mean, right? So we have x. Now, maybe it's x sub I, maybe it's just x, but basically what it means is every item that you have. So if we went back, 5, 6, 7, 8, 9, 10, 11, 12, what's the mean? It's 8.5. So basically what you're doing is taking each item, 5 minus 8.5, 6 minus 8.5, 7 minus 8.5. That's what you're doing right here. Each item minus the mean. You are squaring those, and then you're taking the sum of all those squares. You're going to hear the phrase sum of squares come up a lot in this class. And that's basically what it means. The sum of the squares, these are the squares, and you're taking the sum of them. And then what you're going to do is you're going to divide that by n, uppercase n, the number of samples you have in your population, right? And then you're taking square root of that. Okay, now how does that differ? Well, check this out. When we go to sample standard deviation, it's almost the same formula. Of course, the notation is different. We have lowercase s because we're dealing with sample standard deviation. We have x bar because we're dealing with a sample instead of a population. But we have n minus 1. That's the difference in the formula right there. N minus 1 on the denominator of this formula. So we're doing the same thing. We're taking each item and we're subtracting it from the mean. We're squaring those and we're summing all those squares, the sum of squares. We're dividing that by n minus 1 if it's a sample, and then we're taking the square root of that. Almost the same, but instead of n, it's n minus 1. Why? That's crazy. In fact, why n minus 1 is the title of this slide. Well, the standard deviation is intended to be an estimate of the population standard deviation. I wrote that incorrectly. What I should have said is the sample standard deviation is intended to be an estimate of the population standard deviation. We're estimating. We don't know. We're taking a sample, right? Take a scoop, an ice cream scoop, and we're sampling this ice cream. We're assuming that the whole rest of the ice cream barrel tastes, it doesn't come in a barrel, but go with it. We're assuming that the rest of the ice cream barrel tastes like the scoop that we get. We're sampling it. But we want to have a good estimate. We don't want to underestimate. In fact, it's better to overestimate than underestimate, right? In this case, we want to be more conservative. So we want it to be an unbiased estimate of the population standard deviation. We don't want to assume that it's smaller, because then assuming that the standard deviation is smaller is going to lead to, this is further on in the class, but when we start doing tests to compare if two groups are the same or different, if we underestimate the standard deviation, we're going to get a lot of false positives. We're going to get a lot of times when we say that something is different and it's not. And that's not good. That's not what we want. We want something that has a large enough effect that even if we overestimate the sample size, we can still see that there's a significant difference between these distributions. Okay, so we want an unbiased estimate of the population standard deviation. Dividing by n minus 1 is going to lead to a larger standard deviation than dividing by n. Now, hopefully that makes sense. Let's go back and think about this. Let's assume that the sum of squares is 50. I kind of walked myself into a corner there. Anyway, let's assume that the sum of squares that we have is 50. Yeah, that wasn't a good idea. And the n is, see, the reason this isn't good is because I'm going to say 10. So we have 10. So 50 over 10, this is easy, it's 5, right? So we're going to say that it's the square root of 5, basically, which we could do. It's not important to do that right now. But if this is 10 and this is 5, sorry, if this is 50 and this is 10, then the number that we get here after doing this division right here is 5. Over here, if it's the same, this is 50 and this is 9. And see, this is my problem when I was coming up with that number. It's hard for me to divide 50 by 9 in my head. But you know that 50 over 10 is going to be a smaller number than 50 over 9, right? You know that that's going to be true. In one case, it's 5. In the other case, it's, I don't know, 5.5, something like that, right? So it's a little bit larger. So you can see that the standard deviation is going to be larger by using n minus 1. Okay, so in other words, what we want to do is we want to be conservative in our estimate of the population. Like I said, we don't want to have a bunch of false positives when we start running tests. That's not good, because then we'll be thinking like, look, I found something, and we could end up giving people the wrong medical information. We can end up looking like an idiot because we publish a paper that isn't true, but we weren't conservative in our estimate. So that's why we use n minus 1. Okay, so let's calculate the standard deviation here. We've got 10 values, 8, 8, 8, 7, 6, 6, 5, 5, 4, 3. Now, the first thing that you're going to do is you're going to find the mean. Well, the first thing you're going to do is list each score, but we already have that. So then you're going to find the mean. All right, so the mean here, we're going to sum all of these together, and that's 60. And like I said, we've got 10 items. So 60 divided by 10, hey, it's 6. Cool. Now what we're going to do is find the deviation from the mean. Like we said before, what I'm going to do is I'm going to take 8 minus 6, 8 minus 6, 8 minus 6, 7 minus 6, and so on. And you can see that what we get here is a positive 2, a positive 2, positive 2, 7 minus 6, positive 1, 6 minus 6 is 0, 5 minus 6 is negative 1, 4 minus 6, negative 2, and 3 minus 6 is negative 3. If you add all these deviations up, you should get 0, because if 6 is the mean, it's the central tendency, then if we spread out on one side, that's balanced by our spread on the other side. So we should end up with a 0 if we sum all these together. And that is also the reason why we have to square these numbers next. If we square them, then we're going to get a number that's not 0, right? Because if we square anything, a positive or a negative, it ends up being positive. So 2 squared is 4. 1 squared is 1. 0 squared, 0. Negative 1 squared, hey, that's 1 as well. Negative 2 squared is 4, and negative 3 squared is 9. And then when we sum those squares, remember, sum of squares, these are things that are going to come up again. The sum of the squares is adding up all those square deviations from the mean. And in this case, it's 28. Okay, now this is a sample. So we're going to divide by n minus 1, not n. And we have 10 items, so that means that n minus 1 equals 9. So we're going to put 28 over n minus 1, which is 9. 28 over 9 is 3.11. We have one thing left to do, which is take the square root of 3.11. And that is 1.76. Hey, that's the standard deviation of that set of numbers. That means that we'll expect a 1.76 deviation from the mean of 6 for roughly 38% of the cases. Okay, now variance. Let's talk about variance. It's basically the standard deviation squared. So let's jump back to where we were just a second ago. We did all that work. We took the sum of the squares. We divided by n minus 1. We got 3.11. And then I said there's one thing left to do. We have to take the square root of it. Well, hey, if you're looking for variance, you're done. You don't have to take the square root of it, because before you take the square root, that's the variance, right? Variance is s squared. Well, here's s squared. You're done. Congratulations. All right, so there's this one practice question that I want you to do. What you're going to do is calculate the mean, median, mode, range, standard deviation, and variance for these numbers right here. These are fructosamine levels. Now, to give you a little bit of background, fructosamine is a compound that's formed in the blood. We use it as a marker of blood sugar levels. So this is, something that you might use when you're running labs on somebody to look for, blood sugar levels. Maybe you're looking for diabetes or something like that. You want to take the average of blood glucose for this one person. This is over, let's say, a week. What's their average blood glucose in a week? What's the median blood glucose? The mode, the range, standard deviation, variance. Pause this video right now, and I'll give you the answers after you unpause the video. Did you pause it? I know you didn't. Go ahead and pause it. Okay, welcome back. Here are your answers to check to see if you got it right. The average is 191.3. The median is 189.5. The mode, 210. The range is 114. The standard deviation is 36. And the variance is 1,297. 0.9. Okay. Great. I'll see you in the next video. Here are some... Oh, sorry. We should summarize what we talked about. I apologize. So central tendency and variability are the main measures that we use to describe our data set, right? Again, we're assuming that these are a normal distribution, so we kind of know what that looks like. What we need to know is where the normal distribution is and how wide or skinny that normal distribution is. And that's central tendency and variability. The central tendency describes the center point of the distribution. Variability is the spread of the data. Okay, so here are some extra resources. You have these slides, so you can go visit any of these. And in the next video, we're going to talk about how to do this in Excel instead of by hand. Okay, so I'll see you in that video. Well, I was going to say soon, but when you decide to watch it.